Hi viewers, welcome back to the channel. As usual, today as well, we have an interesting problem in our hands. So let's get started. See, as I tell every time, please try to solve the problem on your own initially, then only see the rest of my video. So, see, this particular problem, you can see people solving this problem in a lot of ways. But my intention is to tell you all the concepts that are involved from a very fundamental level. My intention is not to give you any shortcuts. My intention is to teach you or to tell you at least what are the concepts that are involved in this particular problem and what are the assumptions that essentially helps us in solving this particular problem. So here we have a mass as shown over here, then we have a spring. There is one very important assumption that is given here. They are saying the disk rolls without slipping on the horizontal surface, and they are asking us to compute the natural frequency of the system. Make sense? So once you're asked to compute the natural frequency of system, there are a lot of ways. You can use the energy method, you can use the Newton's second law, or I would rather like to call it the Euler's law, because Newton did all his stuff or all his equations for particles, and Euler kind of came up with equations that can be extended to rigid bodies. So before I solve this problem, I want to tell you a key concept in dynamics, that is, what are the different kinds of motions, or what are the different kinds of general or motions that is possible in a plane. Okay, so the first is linear translation. So an example is a block as shown over here. So this is linear translation. What is so special about translation? See, the concept that you should understand about the linear translation is, let's say in the rigid body, see, I'm only talking about rigid bodies here, I'm not talking anything about flexible bodies. If you have a rigid body and if it is undergoing linear translation, then doesn't matter which point I am talking about, let it be point A, let it point B, the velocity of all those points will be the same. So in this case, velocity of A will be same as that of velocity of B. So that is one important thing to remember regarding linear translation. Now let's go ahead and look into the second type of motion. That is pure translation. Pure translation is already dealt with. Now let's move to pure rotation. So in this particular scenario, say this particular bar is rotating about this pivot point O with an angular velocity of omega. Units of omega will be, let's say, radians per second. Then let's say, similar to the first case, I have two different points in my body which is undergoing pure rotation about the point O, and my interest is, or I'm rather interested in computing the velocity of these 2 points A and B. Then I won't get into the vector notation of that, but in magnitude, velocity of A vector and velocity of B vector are not equal, but they were the same in pure translation, but when it comes to pure rotation, they are not equal. So to give you a little bit of more detail, velocity of A can be written as natural frequency times, let's say, RA, where R is the radial distance from the pivot point O to the point A. And similarly, I can write velocity of B vector as omega times rb, where little rb is the radial distance between the point capital O, this pivot point, and this point B, which is the point of our interest, or the point where I want to compute the velocity. Okay, so this is the formula that connects or that tells us the velocity at different points in a body which is undergoing pure rotation. Now there is something called general plane motion. What is general plane motion? Actually, most of the real life objects that you encounter in your daily life, let it be the wheels of automobile, most of them are undergoing general plane motion, which is a combination of translation plus rotation. I have an example over here to explain the same. Let's say I have this road. Okay, this is the initial configuration, and after a while this particular bar or road has assumed this configuration. Okay, this is general plane motion. So this is not simply translating like this, and no, this is neither translating nor rotating. Actually, it's a combination of both, because this final configuration as shown over here can be thought of as the combination of two motions. The first is, let's say, so this is my initial configuration and this is my final configuration. So this can be thought of as the combination of linear translation plus rotation about a point. I'll explain this in more detail. Let me give some names for the end. So A prime B prime is the final configuration and AB is the initial configuration. Let's say in between I have something like CD also. So what happens here is, initially this bar AB gets translated to the configuration shown here like DC. So these two lines are parallel. I hope that is quite clear in the illustration. So initially it translates from here to here. Then the rigid body is undergoing a pure rotation about this point, about the point B prime or D prime. Both are coincident points. It is undergoing a pure rotation by an angle, let's say called phi. Then it is reaching the final configuration. So in general plane motion, the total motion can be thought of as a combination of linear translation plus rotation. Now what else we need? We talked about linear translation, then we talked about how velocities of different points are related, and then we went to talk about pure rotation. In pure rotation also I gave you equations which can tell you what is the velocity at each of the points. In here also I can give you a similar expression which is not that very straightforward, but I can explain you that. So if you have a body, let's say a bar AB which is undergoing general plane motion, then the velocity at 2 points can be related using this expression. Velocity of B is equal to velocity of A vector plus omega cross RBA, where RBA is the position vector that is directed from point A to point B. Assume that you have two position vectors, RA vector and RB vector, then capital R B with respect to A can be simply written as the RB vector minus RA vector. See, if these vector notations are appearing foreign to you, I sincerely request you to take up a good book in engineering mechanics and understand these things. But for the time being, I want to convey this message that in linear translation for a particular body, the velocity at all points are the same. But once the body starts undergoing a general plane motion, then velocity at two different points in the same body can be different, and they are related using this particular term. See, in this particular expression, if we assume that omega is equal to 0, that means my body is undergoing a pure translation. then you can simply see that velocity of B is equal to velocity of point A. Make sense? So this is the general expression that connects the velocity of different points in a rigid body when it is undergoing general plane motion. So that was a lot of introduction, but I believe that is required before we can completely appreciate the concepts that are involved in the other problem. The next concept that I want to drive home is the concept of instantaneous center of zero velocity. For that, for the sake of explanation, let me take in another example. In this particular example, you have a disk which is rolling over a surface without slipping. Without slipping means, from a definition, without slipping means the point of contact is having a zero velocity. Because your ground is at zero velocity, so the point of contact is also having a zero velocity. This is only possible when you have sufficient amount of friction in the flow, on the flow. I'm not getting into the details of those things. But if that is the case, actually when you look at the problem, it is undergoing general plane motion because the disk is translating as well as it is rotating. So these two are happening simultaneously. But using the concept of instantaneous center of zero velocity, we can assume that for that particular moment, this whole system is pivoted about that particular point called the instantaneous center, and it is undergoing a pure rotation about that point. So for a disk which is rolling over a surface without slipping, this is that I see. So this is our instantaneous center of zero velocity. So what does that mean? If I go ahead and draw a conceptual diagram, then momentarily we can assume that this disk is pivoted about this point as highlighted here, and this is undergoing a pure rotation. See, the complexity of the problem comes down from that of a general plane motion to that of a pure rotation. So we can assume that for that particular instant, it is only valid for that particular instant. That's why it is called instantaneous center of zero velocity. This point is having a zero velocity and this point is only valid for that particular instant. If saying all that, if I ask you to compute the velocity of point A, then you can simply tell me, let's say if RA is the distance, little r subscript A is the distance, then you can say velocity of the point A can be given in magnitude. I'm talking about only magnitude here. It can be given as omega times little ra. Similarly, if you ask me what is the velocity of point B, then it will be omega times little rb. You remember this formula? We have seen similar formula for pure rotation about a pivot point. So for that moment, all these equations are valid. Clear? Okay, that was a lot of introduction before we actually start doing the problem. But I believe it is absolutely necessary you appreciate all those fundamentals. Okay, now the question is to find out natural frequency of the system. So being a biggest fan of Newton, I will always start with the Newton's method or writing the equation of motion of the body. See, since this disk is rolling without slipping, I can assume that momentarily or at every instant, even though the instantaneous center will be changing, I can always write the equation of motion about that particular instantaneous center as shown over here. So then I am going to write down the different forces that are acting on the system. Here is the frictional force and here is the spring force. Now the degree of freedom that I am using to denote the motion is theta. So theta is the rotation. Let's say I have a line drawing from the instantaneous center to the center of the disk. Then theta is the amount by which that particular radial line will rotate. So it will rotate about the instantaneous center. That comes from the definition of instantaneous center. And why there is instantaneous center? That comes from the assumption of rolling without slipping. So see, this is how the concepts come stacking one after the other. That makes the subject so beautiful. So now x, the deflection in the spring, can be related to this particular rotation of the radial line. It is pretty simple. Little x is equal to capital R times the theta. Make sense? Then I'm going to take the moment about the point IC. Why IC? Because it is undergoing pure rotation about that point. That makes my life a lot more easier. That reduces the complexity of the problem from that of a general plane motion to that of a pure rotation. So now if I write down the equation, J1c is the polar mass moment of inertia of the disk about the instantaneous center. That's why the subscript IC is equal to, actually this is the positive direction of theta, but my kx times this distance, which is the moment caused due to the spring force that is opposing the motion. It is trying to bring the disk rotate, or it is trying to make the disk rotate in the other direction. So that's why a minus sign here. Then it's just cranking the mathematical wheel. Substituting for x, little x capital R times theta. Now using parallel access theorem, computing the polar mass moment of inertia of the disk about the instantaneous center, which is mass moment of inertia, polar mass moment of inertia of the disk about the center times the mass times the distance between the instantaneous center and the center, which is CG of the disk, which is capital R. So plugging all those things, we will finally arrive at this particular expression in terms of theta double dot and theta. From this, comparing it with the good old equation mx double dot plus kx equal to 0, we know that natural frequency can be written like this. Well and good. Now, before we wind up this video, I need to show you the solving this particular problem from an energy method also, because I have got something exciting for you. See, when we go ahead and try solving this problem from an energy method point of view, again then I'm first listing down what is the total energy of the system. The first term comes from the potential energy of the spring, quite understandable, and the second term comes from the rotational kinetic energy of the disk. So this is given by half J1c omega square. See, lot of textbook use, lot of convention. Some people use capital I for mass moment of inertia, but doesn't matter whatever notations you use. It's all about understanding what is that quantity and what is the units of that particular quantity. So here J1c will be having the units of kilogram meter square. Okay, so see, you may be wondering why I am not taking the energy component that comes due to the translational kinetic energy of the disk. Think of yourself. See, I am not taking the contribution from the kinetic energy of the disk because at every point, since this disk is rolling without slipping, I can assume that at every instant the disk is undergoing a pure rotation about the point. About which point? About the instantaneous center. Instantaneous center will be changing, but at all instances I can assume that my disk is undergoing pure rotation about the corresponding instantaneous center. That's why there is no translational kinetic energy term in this particular expression. Once again, it is simply plug and check. You can substitute all those values. One other thing, now here also, since this disk is rolling without slipping, that is the only reason why we can write this. That is, little x is capital R times theta. That is because of the fact that this disk is rolling without slipping. That is again because of the fact that for that moment we can assume that the disk is undergoing a pure rotation about the point IC. See, the rest of the things is simply turning the mathematical crank. Then you can take the first derivative of the total energy equal to 0. Then you can cancel out the terms theta dot theta dot. Then finally again you will end up with the same answer. Thanks for watching. So we looked at the concept of what are the different kinds of planar motions that a rigid body can have. We looked at linear translation, pure rotation, and general plane motion. Then we looked at the concept of instantaneous center of zero velocity, and we used all those concepts to solve this problem in a proper manner. I don't want see simple advice before I wind up this video. Don't ever use a formula without knowing its limitations or without knowing what are the applications where this formula is not applicable. Thanks for watching.